Our presenter of the tutorial is Kane, and he specializes in the sciences of electronic imaging and making it possible to accurately reproduce video signals on display devices. These efforts have been the focus of his company, Kane Productions, since its founding in 1982, 30 years ago. Mr. Kane has a long history of participating in standardization of the canvas on which electronic art is created and making it possible for a mass audience to be able to see the art as it was intended to be seen. His work has centered on consumer electronics, home theater in particular, in addition to continued work in the broadcast and post-production communities. Mr. Kane's current focus is on new higher definition formats and better quality 3D images. Now, we would like to ask all the attendees to please move to this corner closer to the display so that you will be able to actually better understand and see what's going on. If you sit too far away, you wouldn't be able to catch all the details. Thank you very much.
Okay. I'm going to take the time to ask everybody, please come up, don't sit in the back row. Please feel free to get up, I don't bite too badly. But anyway, you're going to be able to see what's going on much better if you move forward. So there's lots of seats in here to fill in. And so, and if you're sitting over here, move over here because you'll be able to see things a lot better. All right, the topic of today's presentation is the reality of stereoscopic 3D imaging. And when I say the reality of the imaging, it turns out that we don't have a lot of experience in looking at stereoscopic 3D images. And therefore, when we as either manufacturers or reviewers or first-time viewers of 3D images often attribute things to the image that don't exist. And so among the things that I want to get across today is a practical approach to evaluating the real quality of 3D as opposed to what you think you're seeing. And I want to emphasize that in the process of our television system, or television system or any viewing system, we tend to look at an individual medium and we form an opinion of what that medium looks like, independent of the rest of the world around that medium. There were times in the 1950s when people watched this 1950 Zenith television that they thought they were seeing a terrific picture. Now, by today's standards, you laugh at them and wonder how they ever sat in front of the thing and watched it at all. But they were able to separate the reality of their surroundings, and they were able to look at the image on that black and white TV set and say, oh my gosh, that's absolutely spectacular. And then, of course, in 1954 came color television, and the screen was even smaller. And in fact, when color television was premiered, it's January 1, 1954. It was the Rose Parade from Pasadena. It was the first NTSC broadcast over the NBC network. And this 16-inch display that you see here was accompanied by a 21-inch black and white TV set so that people could see the detail on the black and white TV set and see the color on the 16-inch set. There were multiple cities, hotel demonstrations set up in multiple cities around the United States, and of course NBC broadcasted through the whole network. But it was color, and therefore there was an acceptance of this size of an image. And of course, as we went further, how many of you remember the days when Laserdisc was considered an oh my gosh format? And in fact, I'm actually partially responsible for that. the NTSC system that was on the disk couldn't be transmitted because I was actually responsible for increasing the bandwidth that was on the disk to a point where it truly was better than any signal anybody had ever seen before, yet it wasn't anywhere near reality. And so, but people would still look at this and they would attribute properties to the image that no one had ever thought of. And, you know, in other words, that weren't real. When high definition came along, images like this, when people first saw this sort of thing in high definition, they were absolutely certain it was 3D. When I did my first projected images in 1080p, I had a whole audience believing that I was doing 3D because they were seeing a picture quality that was very much beyond their expectations. They had a preconditioned idea of what an image like this should look like. And because I was presenting them with so much more information than they ever anticipated seeing, what they came out of it saying is, oh my gosh, it's 3D. So part of what's happening is now that we're actually getting into real 3D, people are seeing things in it that they don't understand, that they don't know what's actually going on, and they're attributing properties to that 3D signal that just don't exist. Now, the purpose of today's session is to talk to you about the reality of 3D and try to help you get up to speed with 3D. In other words, get by the wow factor called HDMI. I thought I had this thing fixed. Anyway, the idea is to get by the wow factor of the format and actually be able to look at it for what it is. So, among the things that I want to do is break down 3D into the reality of the format. And this is just to show you what the images are about. But as a way of leading in and supporting what I'm talking about, the whole industry, when 3D first came out, this is the reason I want everybody to sit close. There's a lot to say there. When the industry first started looking at 3D, they were enamored with it, but it was not long into 3D, at least in the motion picture world, that there was good 3D and bad 3D. In other words, people were seeing enough of it to recognize good from bad. And there was quite a concern in the Hollywood Reporter that the studios, now that people were actually getting used to 3D, the studios were going to have to step up and do a better job because people were finally getting used to seeing it in the theater often enough so that they could tell good from bad. That they would know when you had good 3D and you would know when you had bad 3D. Now, the premise behind the discussions that we're going to have here deal with the consumer world. And of course, 3D is coming to the consumer world in a slightly different way than it did in the motion picture industry. We have active displays, we have passive displays, we have issues with the kinds of panels, the LCD panels versus plasmas versus DLP. We have shuttered glasses, we have polarized glasses, we have glasses with color filters in them. We have all sorts of options in bringing 3D to the consumer. The options are so large that oftentimes people look at the images and have no idea what they're actually seeing. So what I want to do is discuss a method of determining what is really good and what is really bad fooled by the fact that, oh, this is new and I don't know what to expect and it's there. There was a time, as an example, with 3D where the motion picture industry said that if it had depth, that was enough. They didn't really care. As long as it had depth, it was 3D, it was saleable, and eventually, of course, the audience got wise to this. And there is a concern now that the audience, as much as they've gotten wise to bad 3D in the motion picture industry, there is a concern that they're going to get wise to bad 3D in the consumer industry. And among the things that I've discovered in my own career is that even the manufacturers of this equipment don't know how to look at the image and don't know how to judge for themselves whether they're doing a good job or whether they're doing a bad job of presenting the information. So what we're going to be concentrating on now, the majority of what we're going to be talking about is flat panel displays, but all of this, of course, would apply to a DLP projector or any other projection technology. But we're going to be looking at evaluating 3D displays. Now, this is another thing where I'm just reinforcing the fact that we're finding that people aren't recognizing errors when errors exist. Now, how many of you are aware of the controversy in passive 3D on LCD displays, where they put up the left eye, they take the full 1080p signal, and they take half the lines out of the left eye, and they take a full 1080p signal for the right eye, and they put half of each image up on screen, and then claim it's full resolution, because 1/2 plus 1/2 is equal to a whole. And this is an example, and there are actually people from the National Institute of Standards who are today saying 1/2 plus 1/2 equals a whole. And they aren't believing their eyes when, in other words, they're just looking at pictures and say, well, it's got to be a complete picture. It's got, it can't possibly be half resolution, half vertical resolution. And so what I'm saying is that we have to take an analytical approach to 3D to understand what it's actually doing. And once we understand what it's actually doing, then we can be better prepared to understand fully what's actually happening versus what we think is happening. Incidentally, this sort of stuff leads you quickly into analyzing it step by step. Really does truly lead you quickly into understanding exactly what's going on, as opposed to having any presupposed notions of what's happening. Okay, so we're going to start out with the fact that the reality of stereoscopic 3D is nothing more, as a starting point, is two 2D images. Does everybody understand that? That basically what we do is we have a left eye image, and there, I don't know how many of you can see this, but there's an L in this one, and there's an R in that one, so that we know that one is the left image and one is the right image. But stereoscopic 3D is, at its starting point, at its core, two 2D images. So if I want to determine what a display is capable of doing in 3D, part of understanding the potential of any display in displaying 3D is understanding it's just being asked to display two 2D images. In the case of a shuttered glass approach to 3D, it's the left image, then the right image, then the left image, then the right image, but it's two 2D images. In the case of the polarized system, it's taking half the lines out of the left image and half the lines out of the right image, and it's presenting the left and right image simultaneously, but there are filters in front of each half line, so that with polarized glasses, 1/2 the lines go to one eye and the other half of the lines go to the other eye. So it's still two 2D images. So in any display, in analyzing any kind of display, if we take a step-by-step approach to figuring out what the display is doing, the best approach is to find out what the display can do with a single 2D image. If we understand what a display is doing with a single 2D image, it's going to give us a clue to what it might do when it's displaying two 2D images. So the first approach, and this may sound silly, but the first approach that is actually going to give you a clue to what's really going on versus what you think is going on is to analyze the display in 2D. Find out what the display can do with a single 2D image as opposed to doing with two 2D images. I'll get that out. So we're going to start with the 2D evaluation, and what I'm going to do is give you an idea. Now, I'm going to pick on the controversy of active versus passive 3D just because that's the biggest controversy in what people are seeing, what they think they're seeing versus what they're really seeing. So I'm going to concentrate on that in particular, but if you have questions on any other part of this, I'm actually happy to take questions as we're progressing through this. I want to, I'm pulling up a disk now that has test patterns on it, and of course the issue with active versus passive is resolution. And so I want to show you a number of test patterns and what they really look like, and of course we would then go into a display and figure out, I'm going to skip all the standard stuff of the normal calibration stuff. And I'm going to go directly to something that involves resolution. Now, one of the things that I found in looking at resolution, this, well, it may not look like a resolution chart. This actually tells me a lot about a sharpness function and how well the sharpness function is happening. So I can go down here, and I want to do this just because very few displays are actually set up right as they come out of the box. Can everybody see the distortion that's being added to the image by turning the sharpness control up too high? Can everybody see that the sharpness control can be turned up so high that you can actually totally obscure the reality of any fine detail that's in the picture? So one of the first things that's happening when we look at 3D sets is almost every single manufacturer has a sharpness control set way too high. So if we're trying to look at the reality of what is available in image resolution, we actually have to pull the sharpness control completely out of the picture before we can know what the display is capable of doing in resolution. In other words, this can get so bad, the distortion that this is adding to the picture can get so bad as to almost totally obscure real detail. So how would you ever know what the display is doing in real detail if there's a control that's obliterating real detail? I'm having fun with words. Anyway, in almost every single set that I've evaluated, the manufacturers have the sharpness control set so high that there would be absolutely no way that you would actually know what the resolution of the display, what the display itself is capable of doing, because the processing electronics ahead of the display is so badly distorting the signal that you can't see what's going on. So the sharpness control is one of the first things that has to be set right. Now, the performance of the sharpness control, you will find on some sets, when you turn it all the way down, you can actually soften the picture. So you have to know when the picture is soft. You have to know what the limit of the sharpness control is. It just so happens that this particular manufacturer, the 0 position is no edge enhancement, no extra edges. So I happen to know that 0 is the right position for this particular projector. Now, there's something else that I find absolutely interesting. How many of you have ever bought a 1080p display and expected it to be able to display a 1080p signal? Has anyone in this room ever bought a 1080p display and expected it to display a 1080p signal? Anyone? Now, how many of you have actually taken the time to figure out whether it does or not? Okay, we got one person. One person? We got one person that's actually checked. Chances are 99.99% as you pick up this display as it comes from the factory, it won't display 1080p. It might be labeled a 1080p display. There might in fact be 1080p in the actual resolution, but it won't display it. Let me show you what most of the sets look like as they come from the factory. That's what most of the sets look like when they come from the factory. Can you see the difference? Can anybody see the difference? Can anybody see that that's not displaying 1080p? So, once again, if we're going to actually determine the real resolution capability of the set, the first thing we need to know is in 2D, can it display 1080p? Chances are, the way it's set up, chances are no, it cannot. So even if you're looking for a 1080p signal, this is part of when people just look at pictures and judge pictures and say, oh gee, the picture looks good. That doesn't look good. And it's only when you put up test signals that you are truly informed of what's going on. Does everybody get my position? That doesn't work. And that's really obvious that it doesn't work. So right offhand, if I put up this particular test pattern and I look at the display and it does that, I know the display can't do 1080p. Now, usually, and it's often hidden, usually in the menu system, there is something that will allow you to get to a point where it will actually display 1080p. Now, in the majority of sets that I've worked with, this option has an obscure name, and it's scan fit or just scan or some words that don't mean anything. They don't logically mean anything. They would not be words you would ever choose to get a 1080p display. So here again, this is part of evaluating the 2D capability of the set first. Because if it can't reproduce a 1080p 2D signal, there's no way it's going to reproduce a 1080p 3D signal. So we have to check. This is a step-by-step approach. Make sure it can do 2D first. Now, the break remote control. I do this at home too. I set remote controls down, can't find them. Anyway, the next test pattern that we're concerned with is one that shows individual horizontal resolution and vertical resolution. So these are single pixel transitions in the horizontal direction, and these are single pixel transitions in the vertical direction. Now, what this does is it tells us how well it's doing horizontal resolution independent of vertical resolution. Now, the test pattern that I was using before, this is actually a combination of horizontal and vertical together. In other words, I've got single pixel in this particular wedge right here. I have single pixel transitions in both the horizontal and the vertical direction. So this is a really tough thing for a lot of displays to do. It turns out that some displays can do a phenomenal job of doing horizontal only or vertical only, but can't do horizontal and vertical at the same time. And so you're going to find some displays that this will be almost visible, it'll be dim, the shade of this will almost be the same shade of that. Yet when you look at horizontal and vertical alone, then what you will find that, gee, they look pretty good. So this tells me that if it won't do this and it will do that, it's still deficient in its ability, because real detail is much closer to this sort of thing. This is the sort of thing that you would get in flesh tones, in horizontal and vertical together. It's not, detail doesn't always come in just horizontal or just vertical. Somehow it comes horizontal and vertical together. And there are a number of display technologies where it's actually much harder to do this than it is to do that. So you have to test for both. You have to actually check for both to make sure that it can do horizontal only, vertical only, or horizontal and vertical together. Okay, just for a reference, this is full resolution. These are 2 pixel transitions, which 2 phases of 2 pixels. So this is half resolution, and this is 1/3 resolution. Now, in some of the projection technologies that I'm working with, this actually turns to black. There's no detail in it whatsoever, and that rectangle turns black. There are a number of technologies where this will turn color. It'll be a color. Does anybody know why this in particular might turn a color instead of be gray? Any guesses? No, that isn't it. Anybody else? Nobody? All right. Here's why it will turn color. DLP is the only digital technology that exists. Every other display technology so far is analog. Analog devices have frequency response. The panels don't have the same frequency response. So if this turns a color, it means the frequency response of one of the panels is better than the frequency response of another panel. Whoopee! Something new every day. Now, not naming names, one manufacturer realized that in their technology, so they filter out all high-frequency information to avoid detail changing color. Obviously, if detail approaches this, it's going to change color, so they filter it all out. Now, they claim that they have a 1080p display, but because the frequency response of each one of their red, green, and blue panels is different, and they know that if there's fine detail in the picture, it will change the color of the picture, they filter all the fine detail out. So, again, if we're measuring detail, if we're trying to find out what displays are actually capable of doing, there's all sorts of clues in looking at 2D to determine what the display is actually doing. So that's one of the issues that needs to be done. Anyway, so now we sort of, from this, we can get an idea of what 2D performance is in resolution. And I'm sticking primarily to resolution because that's been a controversial issue in 3D. But can everybody see now how by analyzing the 2D first, that we have all sorts of clues to what we might expect when we look at 3D? Does everybody get that? That now we've got a huge solid foundation for determining what the 3D display is actually doing. And we don't have to be fooled by the fact that we don't have expectations of 3D and we see things and we think, oh my gosh, look at the depth, it must work perfectly. And that's actually what's going on. People say, oh, look at the depth, it must work. And yet, and they stop right there, and they have no idea how well it's actually functioning. And in many cases, as I've just illustrated here on this set, in many cases there are actually things you can do with controls to actually get a good picture. And so among the things that you have to do is find out what the control settings are to get a good picture in 2D. And then if you don't have 3D test patterns, copy those 2D numbers for adjustments over into the 3D menu. So if the correct position for sharpness is 10 in the 2D mode, put it at 10 in the 3D mode. So you've got to have a starting point. And this step-by-step analysis of 3D helps me understand what's going on in 3D. Now, from this point forward, we'll get there. HDMI. Anybody want to fix that for me? Never mind. Oh. Yeah, please, somebody fix HDMI for me. Sorry. HDCP, I should. Well, actually, I got into discussion of that with somebody at the show floor earlier today. This is all HDCP, so whether it is or not, it has to be. Anyway, so the first thing is that there should be no compromise in what the 2D is doing. Or if you see compromises in 2D, you can pretty much guess that they're going to be in 3D as well. So it's a starting point, but it informs you of what to expect. Or it informs you of what you need to look for when you're looking at 3D. So anyway, it informs you of what's going on. Now, to get 3D, there's a whole bunch of generators on the market. I happen to be using the AV Foundry, and I've picked this particular generator because it's infinitely programmable. In other words, I can create any kind of test patterns I want, and I can put it on an SD card and put it in the generator, and suddenly I have what I want. So among the, incidentally, as much as I put the brand name of the generator up on screen, there are easily 3 or 4 generators on the market that can do this. The shortcoming of this particular generator, it doesn't do motion. And there are more expensive generators out there that actually do motion, that will actually put the pattern in motion for you, that sort of thing. This is, I think, a $2,500 generator. And so, you know, relatively inexpensive. I'm picking it as an example. I'm not telling you to go out and buy it. I'm just saying it's an example of something that can do 3D. And the reason I'm saying that is there's not a lot of availability of 3D generators. There's not a lot of availability of test patterns for you to check out what 3D is doing. This happens to be the simplest, straightforward, static testing device for a nominal fee that's out there. So, as I said, I'm losing the room. Oh, again. So, among the things that I want to do is to give you an idea of some of the. There is some flexibility in this generator. It's rather significant. You can start out. This is why I wanted everybody to sit up close, because I can't do anything about the size of this. The size of this interface. There are no controls on the generator, so all the controls are graphic user interface on the computer. So, but it becomes convenient. If you look at this, the generator has all sorts of rate options. In fact, including set your own. You know, figure out what you want to do and create your own rate. So there's all sorts of options in rates you want. Now, in this particular case, the majority of source material in 3D is 1080p 23976. So that's what the 23 means, 1080p 23, for anybody who can't read it. This has a capability of, if it's generating its own test signals, it has a capability of encoding. All my test signals are in the red, green, and blue domain. And if I'm coming out YCRCB, I can encode them as 601 or I can encode them as 709. Got that choice. So there's a fair amount of, I don't want to belabor this, there's a fair amount of flexibility. At the moment, I'm outputting RGB 444. Does everybody know what that means? Does everybody know the difference between RGB and YCRCB? Do I need to? Okay. Red, green, and blue. When we start out if we have a camera shooting light, it's broken down into red, green, and blue. And so the primary source of all of our video images are red, green, and blue. We use red, green, and blue because that's what we see. We only need to communicate 3 channels of information because that's all we see. So primary is red, green, and blue. But in the television system, we initially had a requirement to be compatible with black and white. So we add red, green, and blue together. Of course, you get black and white when you add red, green, and blue together. And that signal is called Y. So if I send a black and white signal down the line and put it into a color TV set, I'm going to get a black and white picture. In order to get a color picture back, I've got to have 2 more pieces of information. If you remember from basic algebra, if you're trying to solve for 3 unknowns, how much red, how much green, how much blue at any given time, you have to know, you have to have 3 equations to solve for 3 unknowns. So there has to be 2 other pieces of information. So those 2 other pieces of information are the color difference signals, the CR and CB signal in the digital domain. That's the YCRCB domain. So everything is transmitted in YCRCB. All MPEG encoding, all of your content is in YCRCB, and then it gets decoded and converted back to RGB. But since I have the choice here of starting out in RGB, I can go RGB to RGB, or I can go RGB, YCRCB, YCRCB into the set back to RGB. So in this case, I'm going into the set. Just a moment. Sometimes I don't know how I'm going into the set. So well, when I put the generator back up, all I have to do is put up the information screen. Out of my computer, I'm feeding RGB into the display. So, and it so happens this is a 10-bit 444 projector. Anyway, so you have lots of options in output, and then if we go to patterns, you'll end up finding that I've created hundreds of patterns. And I've literally created hundreds of patterns for 3D because there's a whole bunch of things to test. So this generator can put all that stuff out. Let's see, if I switch over to the generator, see what it's doing now. Oh, no signal. That's not nice. Oh, there it goes. Well, guess what? My famous and my infamous pixel phase test pattern is what's coming out of it now. In this particular case, it's looking at the left image. Now, this is not a stereoscopic display, so when I put stereoscopic into this projector, it just looks at the left image. And so I'm actually putting stereo into the projector, but it doesn't know that. So it's only looking at the left image. If it were looking at the right image, you would see an R over here. in the majority of the test patterns I created, I actually labeled left and right, so that if you block the left eye, you should see the letter R. If you block the right eye, you should see the letter L. And that makes sure that your glasses are in sync with the picture. So almost all of my patterns have an L and an R in them. So the left panel is labeled left and the right panel is labeled right. But all of the same test patterns that were critical to determining what the display is doing in 2D, I now have in 3D. Now, there's something that is also unique about these test patterns that you need to know. What I'm doing with a number of the test patterns, I'm making them what I'm calling 3D flat. Now, in 3D, you can have things in the plane of the display, or you can have things that are behind the display, or you can have things that are in front of the display. If the left image and the right image exactly match each other, the information is going to show up in the plane of the display. If the left goes left and the right goes right between the two images, the object will appear to be behind the screen. If the right and left cross, in other words, if the right image goes left and the left image goes right, it will appear to be forward of the display. So I can actually manipulate pieces in these test patterns, and I can make them either in the plane of the screen, or I can make them behind the screen, or I can make them in front of the screen. Now, in the step-by-step analysis, the first place I want the images to be is in the plane of the screen. Does anybody know why I want the images initially to be in the plane of the screen? Anybody? Or said another way, I can see what the display is doing in 3D without glasses. So this gives me a tremendous advantage, because now I can separate what the display is doing versus what the glasses and the display together are doing. So that I can actually, anything that's in the plane of the screen, I can fully analyze that information just as I've been analyzing it in 2D, and I can determine exactly what it's doing, what kind of resolution I've got, what the picture looks like, and I can do it without the glasses. So now I know what the display itself is doing. Now, how many people believe that if you put glasses on, you can get something out of the image that didn't already exist before the light hit the surface of the glasses? Does anybody understand what I just asked? If you've got light coming from a display and you put glasses on, how many believe that the glasses can actually add something to the image? Glasses can't add anything to the image. They can only subtract. That is something that is absolutely critical in understanding what you see. So you do this. You put the glasses on and off. If the picture is different with the glasses on than when the glasses are off, that means that the glasses are taking something away. They aren't adding anything to the image. Does everybody understand my position? There is nothing the glasses can add to the image. They can only take away. You can certainly, but in analyzing the image itself, in other words, what's happening is people are putting on the glasses and saying, "Oh, look at all the resolution." I'm saying, what? They literally think when they put the glasses on that suddenly there's new resolution in the image that they've never seen before. And I'm saying this is all part of the concept of people don't understand what they're seeing. It's part of the reason I want people to take a step-by-step approach to analyzing 3D. Because if you think about it, when you put the glasses on, there is nothing those glasses can add to that image. The glasses cannot add detail to the image. Yet there's a huge number of people that put the glasses on and say, oh, look at all the detail that's now in the image that wasn't there before. If you take this step-by-step approach, you understand that's not possible. And so people, this is what I'm saying, is the expectations of 3D are so unknown that when people put the glasses on and see something different, they don't recognize that it's less. They recognize it's different, therefore they attribute properties to it that don't exist.
I think that from experience, you have a huge disparity before people wearing glasses. So they are looking for a very ugly image. And when they wear the glasses, they look to the ways of work.
They look to the...
I see, if you are display an image that has non-zero disparity, you see double.
Yeah.
And then people are arriving to the room, see double. And when they wear the glasses, they see one image.
Yes, especially, but part of the reason I want to start up with 3D flat is because there's no disparity left to right, and therefore I'm giving them an opportunity to understand what's actually happening versus what they think is happening. And yes, I agree that they put the glasses on and they see depth, and they say, oh, look at that, it works, and there has to be lots of detail because it works. Well, you can prove that the detail isn't there. And part of what I'm saying is we've got to get by the wow factor. If we're ever going to actually understand what 3D is delivering, we've got to get by the wow factor. And the way to get by the wow factor is to take it step by step. And that's why I'm proposing the first step of analyzing 3D is what I call 3D flat, meaning that everything is in the plane of the screen, meaning that the left eye and the right eye is exactly the same image. And at that point, when we put the glasses on and off and we see a difference, it makes it really easy to understand that any difference that we see in the resolution of the image has to come from the glasses taking something away, not putting something in the image that didn't exist before the light ever hit the glasses. And that is a help. That is a major help in getting people to understand the reality of 3D as opposed to this phantom stuff. They don't know what it looks like, so it must be. So what we're doing with a lot of these images, in the 3D flat images, the left eye and the right eye are exactly the same, and so we can put the glasses on and see that, especially in the passive system, there's a huge difference in the picture at a particular viewing distance. This is something else where we're getting into a lot of trouble with 3D. Part of the reason I wanted to have you sit closer to the screen is so you could actually see the detail of the screen. Now, the majority of you, in fact, I'm guessing all of you, can't tell that there are single pixel transitions going on in this wedge. This wedge probably just looks like a flat wedge to you. Anybody care to get up and see that there's actually transitions in this? You're welcome to if you'd like to. There's actually single pixel transitions. This is not a flat. Piece of light. There are actually single pixel transitions in that light. And what happens is as you get further and further away from the display, you can't see the detail in the display. Now, one of the manufacturers that's designing a passive 3D system is recommending a minimum of 4 picture heights. Well, at 4 picture heights, it's far enough away so that some people don't have an ability to see the detail in the picture. And so they don't know it's missing because they're too far away from it. Now, with this projector, to give you an idea, when I normally watch images with this projector, I sit at 2.5 picture heights away from the image, 2.5 picture heights. The SMPTE and ITU have agreed on 3 picture heights. And so viewing distance also becomes really critical to analyzing what's actually happening versus what you see happening. Now, the manufacturers of the display that are the passive display recognize that and recognize that if you're far enough away from the display, you'll never notice that the detail isn't there. And therefore, they can claim full resolution because you're so far back you can't tell whether it's there or not there. And so that's actually another issue that has been clearly pointed out by one of the manufacturers that's making passive displays. Well, nobody sits that close to a TV set anyway, so nobody's ever going to notice that anything's missing because they're too far back to see any of the detail. And so viewing distance is a critical part of evaluating what a display is capable of doing. And you actually have to be sitting close enough to the display so that you can actually see the real resolution of the display. This display happens to be really good at displaying imaging, so 2.5, I really get what I consider an immersive experience looking at 2.5, and I know at 2.5 I'm seeing every bit of detail that's in that source signal. And so I like sitting at 2.5 to watch this particular projector. Okay, so those are a couple of critical points in doing it. Let me get back to my PowerPoint presentation. We'll see how well the HDMI comes along. Here, we'll get there. A brief pause in the conversation while we get HDMI to work. Okay, so we'll go back to the PowerPoint presentation and pick back up where we left off. And again, I emphasize that that generator just happens to be a single thing that's on the market. There's lots of other options. If you're really truly into this, make sure that you get an option where you can create your own test signals. Because I'm going to show you circumstances where you're going to come up with things that it's really neat to be able to say, oh, I wonder what happens if. And you just sit down and you create the if and go look at it. And I've actually learned more about 3D because someone asked me a question, and I said, well, let me create a test pattern to check that. And then suddenly it's like, oh, here's the answer. And I had no idea what the answer was. You know, I just had to create the pattern to take a look. Anyway, we've got 3D flat allows you to evaluate the 3D display. Now, I've created patterns as they're not showing up in PowerPoint all that well, but where I have separate horizontal and vertical, and there is a pixel phase in there, but didn't quite show up when I put it in PowerPoint. But anyway, what I do is I label the L and R in the panels so that, again, I can make sure the glasses are synchronous, and this is a flat, it's a flat pattern. Now, the pixel phase, you've already seen that. So the flat patterns are left and right. Now, I've already talked about putting the glasses and putting the glasses on, taking the glasses off in a 3D flat image, and keeping in mind that the glasses cannot add detail to an image. I mean, there's no way the glasses know where the detail is in the image, so there's no way they could actually add detail to the image. So, the next part of the evaluation comes in looking at 3D with depth. Now, this is the point where you have to put the glasses on. But if you've been pre-informed by 2D and 3D flat, you're now going to know what's going on when you look at 3D. Now, I'm going to only be able to show you left and right images. Now, what I've done, again, I've labeled the left panel left, and I've labeled the right panel right. Now, in this particular image, at the top of the image, the right goes right, and the left goes left. So, when you see this in 3D, those vertical wedges are actually behind the screen. And of course, at the bottom, they go in the opposite direction. So that when you go left, it goes right, and when you go right, it goes left. So those are forward of the screen. So what you've got is something behind the screen, something in the plane of the screen, and something forward of the screen. Now I get to look at vertical resolution in all three planes. And I still have my reference of vertical information in the plane of the screen. So I know what it, you remember, I know what it looks like in 3D flat because, and I'm providing you with a reminder of what it looks like in 3D flat. And so now we can evaluate the kind of resolution that we have in front of the screen and the kind of resolution that we have behind the screen. Incidentally, I've actually calculated these test signals and calculated the split, the left and right, so that they exactly line up. I'm not trying to introduce any skew in the numbers, so that I need to make sure that these legitimately represent solid signals that are behind. I'm not trying to create a signal that is bogus in some way. They've literally been calculated to make sure that they're legitimate behind the screen and they're legitimate in front of the screen. And that was part of the calculations that we did. And it's actually pretty simple. If you're creating your own test patterns, you just need to make sure that you go left and right an exact amount. In other words, you start from the center, you take the left 6 pixels, and you take the right 6 pixels. At that point, they're an exact match. If you take the left, by 6 and you take the right by 5, then you've shifted the position. It's no longer centered, and so it might not match up. So in creating all these test signals, I made sure that they were legitimate in being behind the screen and being in front of the screen. So,
sorry, why is there a split
okay, the reason for this, if you can see, this is 2 lines. Unfortunately, in the PowerPoint presentation, it's not showing up, and the full resolution isn't showing up. But if you look at this carefully, this is actually 2 line transitions. And so I've got 2 lines on, 2 lines off, 2 lines on, 2 lines off. Now, if I'm actually missing resolution between left and right eye, the fact that one side is shifted versus another, I can see what's missing. In other words, they're out of phase with each other. They're 180 degrees out of phase with, vertically, they're 180 degrees out of phase with each other. So if I'm truly missing half the information, if it was in one place, I might not notice that it was missing. But if it's in both places, then I can really tell if it's missing or not missing. Yeah, well, yeah, but I'm putting them out of phase so that no matter what, the point where the information is missing, one or the other is going to hit that point where it's missing. That's the reason they're out of phase. Logically, if I'm taking half the information away, I could actually position those things so you'd never notice that half the information was gone. But if I slip them, if I make them out of phase, then I'm guaranteed, if the information is missing, I'm guaranteeing that I can see it. So a little thought goes into creating these test patterns. And, well, when you're looking for half the information going, you really do think about the fact that I got to make sure that I can see it. So I offset the phase, and that's why there's a skew in the test patterns. So among the things that has been purported in 3D imaging is So in the process of creating these test patterns, if you notice, as an example, in the right image, this is a solid block, and in the left image, the word left is written in it. So, and I did this on purpose because there's a whole bunch of people that say the left and right image add together. So, the theory is that if left and right images add together, and I didn't include pictures of this, but if you don't have the glasses on and you look at this image, what you're going to see here, the word left is going to be in gray, because in the right side of the image, there's a solid white behind that word. So, full and nothing added together is 50%. 0 and 100 is 50%. So, if you don't have your glasses on, the left appears to be gray. If you put the glasses on, the left appears to be dark. It suddenly goes dark. Now, what this says is that the image, this immediately informs you the images aren't adding together. Because without the glasses, you see gray. With the glasses, you see black. What happens is the left eye can differentiate. The left eye can literally see that it's black. The information coming to the left eye says it's black. And so it literally informs you that it's black. And so when you put the glasses on, both the left and right words, turn dark. They go from gray to dark. Now, this immediately informs you that in seeing 3D, there is at least some differentiation going on, or some complete knowledge of what's happening in each channel independent of the other. The mere fact that this turns dark tells you that the brain fully understands that it's dark. And it fully understands what's going on in the right eye, independent of what's going on in the left eye. Now, initially I was told, well, that's just luminance. So what I did is I created some color patterns. And of course, in doing this, I got really nasty. If you look just at the top left-hand corner, you can tell that those two colors are complements of each other. Obviously, this is blue and green, and this is red. So if they are on top of each other, if you look at these two images without the glasses, they appear to be gray, because blue, green plus red is equal to gray, and they actually appear to be gray. Put the glasses on, and you can see both colors. And you're fully conscious of the fact that both colors are there. You do not see gray. You don't see gray. You see both colors. So it makes it clear that the eye is differentiating the brain is differentiating what's going on in the left eye and the right eye. And I'm actually proposing that it's the differential between the images that gives you your 3D image, not the sum of the images, as everybody's saying. Now, if you go out in the academic world, you're going to see lots and lots of papers that say you see 3D by summing the left eye and the right eye. And so the very first thing somebody asked me, is that what goes on? I built test signals to check it out. That's the reason I think you all need a programmable generator, because somebody's going to ask you a question, what happens if? And that's what everybody did to me. They said, well, what's actually happening? And so I created these test patterns so that I would have an idea of what's going on up here. And of course, if you're actually sitting close enough to the polarized set, when you put the glasses on, you can see half the lines are missing. You can literally see it. They're gone. That it's light, dark, and you can literally see it. It's gone. And it's gone in one phase on the left eye, and it's gone on another phase on the right eye. So what it actually looks like is this. But what the brain does is it doesn't like that discontinuity. So the brain is doing something, and it's obvious that it's doing something. The brain doesn't like that discontinuity. So what the brain does is this. The brain actually lines them up. So when you look across, you literally see one line is missing and one line is there. And of course, if you get back far enough away from the set, you can't see the resolution to begin with, and therefore you don't know that the resolution is missing. So there are things like that going on. I've done some other test patterns. This is just an example of shifting elements within a picture, some forward, some back, and of course labeling left and right. Now, and you can't see it from where you are back there, but among the things that I've been doing is taking out half the lines in a picture and then seeing if I can get that to line up. And if I take the half the lines out of the right half of the picture, in other words, take odd out of the left and take even out of the right, I can put this image up on some sets and get a blank screen. And even though there's information in the picture, I get a completely blank screen because the lines clearly are filtered out. There are some sets that literally date half the lines off. And so if I create a test pattern where in the left image they're showing you the odd lines, so I put the information in the even, and then in the other one I put the information in the odd, and when it gates the lines off, it literally shuts off the picture. Even though the picture's there, it literally shuts it off. And that was another tool I used to prove that half the information is missing. And I can actually pre-program the signal so that when I put it up on the display, the whole image is missing. Yet, when you look at this on an active display, yeah, it's dim and there's a line structure in it, but at least the image is there.
You know, do you have a comment for, because in addition to 3D, a lot of these sets actually have motion compensated rate conversion from 3D. Does that play any of this?
All right.
Reduce the resolution?
The question is, if you didn't hear it, some sets have motion compensation circuits. They give you options in the user menu, and you'll know which set I'm talking about when I tell you is off, low, and high are the three options of the true motion. Now, the interesting thing is the manufacturer describes what those things do. But if you put test patterns in and look at what they do completely different things than are described by the manufacturer. And off isn't off. Off is a fully active position. And so true motion off, and gee, it's in the off position, there's some significant video processing going on. And so the only comment that I have about those kinds of controls is it's fairly easy to figure out what they're actually doing versus what the manufacturer claims they're doing. And in a recent situation, somebody asked me, somebody read the description of what these controls were supposed to do, and my reaction is, I would have never guessed. You know, based on actually testing them and trying to find out what they are actually doing, I never would have guessed that those names that the manufacturer applied to them could have possibly had anything to do with reality whatsoever. So that's another thing about testing displays, is that you literally have to do it to find out what the reality of what somebody is doing. Now, are there questions up to this point?
So Joe, when you were putting up like the red on one side and the blue or the cyan on the other side, do you think the fact that your eyes are seeing different colors in the same spot is what leads to the eye fatigue and the headaches and stuff like that?
Oh, okay. The question is, in the test pattern where I had red and cyan together, and the fact that you can see both, is that some part of what leads to eye fatigue? That particular pattern, absolutely, it leads to eye fatigue. because the brain is trying to figure out how it's possible that that could be happening. So there's no question that things like that lead to eye fatigue. Now, hopefully you know that people who produce 3D content are sort of aware that those kinds of things happen. And so among the things that they often do is try to avoid those kinds of things. They try to look at what their scene content is, and they actually try to simplify scene content so that you don't get any of that stuff happening in the pictures. And there are times when the left and right image are separated so much that there appears to be a discontinuity. In many cases, they will move the image to correct the continuity. This happened in Avatar, and I got a chance to sit through a whole correction session where they just decided that the separation didn't look good, so they moved the images just to reduce the kind of fatigue that we were talking about. So that all comes, reducing the fatigue all comes in the process of production, and it's a conscious part of production. It's also a part of bad 3D versus good 3D. Any other questions? While we're here? Okay. The next topic that we're going to take up is ghosting. There are actually things that are particular to 3D alone. In other words, you don't ever see ghosting on a flat panel display. Well, you do. You see blur on a flat panel display in 2D, but you don't see ghosting. So, okay. So, I ended up developing what I thought was a fairly simple way of looking at ghosting. Now, if you look at this image, everything that's going on in the center of the image is actually behind the screen. And so what happens is if there's ghosting, these diagonal lines will have a second diagonal line along with it. First of all, does everybody know what ghosting is all about? All right. Ghosting occurs, first of all, you have a left image and a right image. Ghosting occurs when information from the left image gets into the right eye. Well, how's that possible? In an LCD display, I'll pick on them in particular, you may know that there's lag in an LCD display, that you put up an image and it stays up longer than it should. So there's a potential of ghosting in LCD if the left image is still up when the right image comes up. In other words, it's the same thing as blur. So that's a potential. There's a potential of crosstalk in the glasses. If the glasses aren't timed exactly right, a little bit of the left image will get into the right eye, or a little bit of the right image will get into the left eye. Or, in the case of the passive glasses, viewing angles. Now, in the passive glasses, and I didn't illustrate this, but I think you all know that there's a filter that goes on the front of the display, and there are lines in the filter that every other line is polarized circularly in one direction, and then the other lines are circularly polarized in the other direction. Well, it turns out that this filter is spaced away. If the actual light-producing device is here, it turns out the filter is spaced away from that, from the light-producing area. It has to be. You know, it can't be right on top of the lines. Well, what happens is there's a parallax error, so that when you are looking in from the center and looking up, then because of the distance differential, the lines aren't in the right place. So what they do is they literally move the lines. At the top, they're moved down. At the bottom, they're moved up to compensate for the fact that you're looking down at it, so they move the lines up, just so that they line up. And of course, they move the lines in the filter down at the top, so that when you're looking up, well, if that offset only works at a particular viewing distance. If you're at any other viewing distance, that offset doesn't work. And so what happens is, in those cases, the lines are in the wrong place, the filters are in the wrong place. So your eyes literally see part of one image, and you'll see it at the top and bottom of the image. Now, that's part of the reason that this particular manufacturer recommends that you be way far back, because if you're way far back, then all the lines will appear to be in the right place, and the ghosting has been minimized. But of course, at that viewing distance, you can't see the detail anyway. All right, so there is ghosting because parts of the left image get into the right eye and parts of the right image get into the left eye. Well, can you see that there is an offset between the left and right? You can see there's a position offset. All right, so what happens if one of these is ghosting? It's going to be offset from the primary line because it's obviously placed elsewhere in the other half of the picture. So the ghost is going to appear to be parallel to the line on either side of the line. And I did this in the diagonal to make sure that we knew which way the ghosting was going. This informs me of actually what's happening. Anyway, there will be an amplitude to that ghosting. In other words, the ghosting will be a fraction of the primary amplitude. So what I end up doing is the ghosting crosses the grayscale. Now this is just a simple approach, but the ghosting crosses the grayscale, and there's a point where it crosses the grayscale that the ghosting disappears because the level approximately matches the level that's behind it. So I can tell, okay, there's 30% ghosting. You know, the amplitude of the ghosting is 30% of the primary, because when the line crosses over here at 30%, it essentially disappears, or when it crosses on 25, it essentially disappears. So within 5%, I can get a quick idea of what the percentage of the ghosting is. Now, to no surprise, it turns out that it's amplitude sensitive. Your ability to see it is amplitude sensitive. So you have to look at ghosting in both the top end and the bottom end to determine what it's doing, and they'll look different. And so what I did is I created a pattern that was the inverse of the first one, so I could see what was going on. And it turns out that I had to make the background gray so that I could actually see what was going on. That was a surprise. You know, when I did the first pattern, it was 100% across. Then I couldn't see what was going on. So I realized I had to make the background gray so I could see what was going on. And then that's the inventiveness of these patterns. Now, this is just there are actually much better ways of measuring ghosting than what I'm doing here. But a year ago, when somebody asked me what ghosting was, well, let's go measure it. Let's go look at it. And so I invented a pattern that allowed me to very quickly look at ghosting. And this only gives me an approximation. And then, of course, as I just pointed out, I discovered with some sets, ghosting can be much worse in one area of the set than another. And, of course, this doesn't work for that. This looks at ghosting over the entire image area instead of parts of it. But it didn't take, building this, it didn't take me long to figure that ghosting could be different in different areas of the picture. So those are the kinds of things going on.
Sorry, in that last pattern, when you alternate between the left and right eye, it looks like you have a fixed pixel width. We have a pattern where it dynamically grows
I have done that. The answer is, the question is that the width of each one of these lines is the same. Have I done test patterns where the width of the line changed?
and the jump between, like as you go left and right.
Okay.
That looks fixed.
Okay, that I have not done. I have not changed the width between the left and right eye. I've not done that. Again, I'm trying for symmetrical things. I'm trying to create patterns that are not bogus, or at least in my own mind, bogus might be the wrong word, but I'm trying very hard to create test patterns that represent what I think, mathematical points in the image where everything should be correct. If you do it right, it should be absolutely correct. So I'm not trying to introduce some offset between the left eye, some offset in image size between the left eye and right eye, because in my own mind, initially, I think that's going to create some sort of a crosstalk. It's going to create some sort of false image that I don't know how to interpret. I don't know what it, I just don't know what it means.
So right now, that offset, that center image is pushed into the screen or pulled out?
The offset, if you look at it, this is the left image and it's left, and the right image moves right, so it's behind the screen.
I have one question. What do you think how precise your value of ghosting is when you look on your screen? Because I think you present...
I'm sorry, I'm going to have to come back. I'm not hearing the question. Can you repeat the question, please?
Yeah, I just was asking myself, how precise do you think is your ghosting value you get? Because what you have here is the value based on the input value. But all the processing down to the screen, gamma is one of those, may change these percentage values. So then you read ghosting is maybe 5%, but it's based on the input value, not on the,
all right.
on the screen value.
The quick answer to your question is you're right. I'm not taking processing into account. But the question being asked is that I'm assigning values here, 95%, 90%, all those values. I'm assigning those values actually based on a linear system. And then, of course, there's gamma correction when you get into this. So that, as an example, 2.5% above black is a barely noticeable difference if you've got a gamma of 2.4. But if you have a gamma of 2.2, there's a huge difference based on gamma. And so, are these numbers accurate? These numbers are only accurate at a gamma of 2.4. They can only be accurate at a single gamma point. And if you're running any other gamma in the display, these numbers are not right. And part of the reason they're in 5% steps is because I knew that I wasn't going to get any more accurate than that. Or at least I didn't feel at the time I created this test pattern I was going to get any more accurate than 5%. So you're absolutely correct. Gamma is one of the things that can affect it, but you're absolutely correct that these numbers might not be right based on the video processing in the display. It's absolutely correct. Anything else? No questions in all of this? So far in what I presented, does any of this make any sense to you? Does any of this create some logic to make it easier for you to understand what's really happening in 3D? Because that's the purpose of this, is to help you objectively evaluate 3D as opposed to subjectively evaluate 3D. How are we doing on time? I don't know where I am. 15 to 3:20? Okay.
About 15 minutes.
So I got, what, about 10 minutes?
About 15.
15? Okay. I was sort of planning on arriving at a point where I was going to take questions, but I can join. Yes. Yes.
What sort of settings do you have where it's using that star mode where it's done sort of where it's color wide
I don't have any special patterns difference in the way that processing happens. There's one of the test patterns that has color saturation in 5% steps, from 5% to 100%. And so I can look at color saturation, and I can look at it as at a reference. So I can go into red, green, and blue. Let me see if I can put some of that up.
I'd be curious, like some formats have offered some sample chroma.
Now, I'm not, I will be honest with you, as much as, and I kind of hope this presentation has been relatively simple. Up to this point, I've only been interested in simple things. There's so much that has been revealed by doing simple analysis that I haven't gotten to anything complex yet. Let's see if I can find some of the color patterns that I'm not doing that much in other things at the moment. Let's just go back to 2D patterns and let's see if I can find color steps. Color saturation. So what you're going to see on the screen, it takes the generator some time to load these test patterns. What you see here is a reference. Now, what I can do with this is look at the decoder and see if the decoder is linear. And so what I do is I go into the projector and I look at blue only, and there's way too much light on the screen. But you can see that the blue decoding and the reference match all the way from 100% all the way to 10%. So this tells me that, at least in the blue channel, my decoding is really linear. So if I go to green channel, you can see that my decoding is really linear. I don't have problems in decoding it at various levels. And then, of course, if I go to the red channel, again, I don't have problems in any kind of linearity. Now, I apply this to a lot of sets and discover that decoding at one level is one thing and decoding at another level is something completely different. So I created this pattern so that I could take a look, take a quick look. Obviously, this is only in 10% steps, but I could take a quick look at decoding and see if it's linear from black to white. And those are the, again, this is simple stuff. This isn't, I'm not doing anything, that's complicated. So, the rest of what I had in part of the discussion is that once you have understood, once you've tested the display and understand what it's actually doing, then you can go put up real motion material, put up any movie you like to watch in 3D. Once you are informed of what the display is actually doing, you'll start seeing that in real material. Where before you were informed of what the display was doing, you were imagining other things going on that weren't actually going on. Does everybody, in other words, you have no concept of what 3D is supposed to look like, so you're guessing what's going on. But by going through all these kinds of steps, you're now informed. You're intelligently informed of what's going on. And so when you start looking at content and you start seeing things, you know what's actually happening. And this is how I get over the wow factor of 3D. That's actually what this whole thing is all about, is how to quickly solve the wow factor of 3D. And actually understand what's going on. So, the rest of any discussions, as I said, I was trying to leave 10 minutes for a question and answer period, and then let you know that there are lots of other things that can be tested, lots of other things that can be done. But is doing, and you start asking questions about particular parameters or what do we see, you create test patterns. And I think that in our world today of building products, I actually think the use of test patterns is becoming a lost art. I don't see a lot of people using test patterns. Give you an example, there have been controversies about refresh rates on LCD displays. And the controversies just rage and people guess and whatever. And gee, you develop test signals and then you photograph the set and you can tell exactly what it's doing. And I am a believer in the scientific approach to things, that if you want to know what's going on, you build test patterns to determine what's happening so that you can be intelligently informed of what's happening. And you're going to have much better products when you know what's going on as opposed to when you're guessing what's going on. One of the things I didn't ask in this, in putting this all together, how many of you represent manufacturing? Okay. Okay. Who else? What does everybody else represent? That's what I thought it was. University. Okay. Some of the other. Anybody else? What are you representing?
Slaves to manufacturers.
Oh, okay. Not quite sure what that means. That was.
Silicon providers.
Oh, okay. You make components for. Oh, of course. If I read the sign, I would know. Anybody else? No. Okay. Yes.
I enjoy your approach that was to divide things into smaller things, be able to understand what's happening there, but all your scheme were based on left and right. Can you tell anything about the ultrasonic displays where information is texture and depth? Have you
Where the picture is.
texture?
Oh. Autostereoscopic.
Because the pattern should be different.
Right. All right. I have not gotten into autostereoscopic. No one has ever asked me to evaluate an autostereoscopic display, so I haven't had any opportunity, I haven't had any reason to look at it to determine what I have to build to determine how well it's functioning. Again, all of this, everything I've done up to this point is, as an example, understanding that stereoscopic 3D is a left image and a right image. And so once I understand that and I understand divergence versus cross divergence, once I understand all that, then testing for that domain becomes really easy and really straightforward. I have not gotten into the mechanics. As an example, I'm told autostereoscopic often divides the picture up into 9 or 10 different areas, and therefore you might need to test 9 or 10 areas individually to find out. In other words, you need to build a test signal that's specific to a position in the picture. And I haven't yet taken the time to study autostereoscopic enough to know if I have to build patterns that are specific to the position in the picture. But I believe that I do.
Worse than that, because you give it an image and the processor in the middle figures out what you want to extrude. You can actually put in, I want this going on this view, without reverse engineering how they go from point A to point B.
Yes. And of course, if I were to be commissioned to do this, I would end up finding out the hard way, because I would end up creating test patterns and noticing that the processing was doing something to me that I hadn't anticipated.
There is a very fun story of autostereoscopy that you can vary the wall factor, you can diminish or increase the depth.
Mm-hmm.
In every monitor, depending on the quality this effect is worse or better, the quality increases as you reduce the depth factor, and the quality is maximum when you have a flat.
Yeah. Well, I stand before you to tell you that I have a lot to learn. But I'm also standing before you to tell you I've learned a lot. And I'm trying to communicate some of the things that I've learned.
Now back to stereoscopic and your measurement picture for the crosstalk. Have you ever thought about putting different measurement zones, because the crosstalk is maybe not equal over the screen, especially on LCDs? We discovered that due to the different heat on the screen, you have different crosstalks over the screen.
The answer to that is yes. The moment I created the first pattern, I realized it didn't work. In other words, I realized that there was a problem in different areas of the screen. So I ended up realizing that I had to completely rethink how I was building that test pattern. So what you got to see here was the first generation of the test pattern, and I haven't gone a lot further than that. There's a lot more things that I've got to do. But and to be honest with you, I got pulled off 3D and got put into 2160p. So for the last 6 months, 3D has been on the table and has been actively on the table, but so has a huge priority on 2160p. So I'm now producing content in 2160p. And incidentally, the content that I showed you at the beginning of this is actually down conversion from 2160p. I had to down convert it so that I could do some tests of 2160p versus 1080p. So I started out at 2160p, down converted to 1080p, and then compare the original versus the up converted. So that becomes the new focus on creating new is 2160p, and all the controversies about 3D still exist, but the thing that really interests me about the controversies in 3D, the majority of what I'm encountering is basic. There's nothing complicated about what I'm being asked to look at. And so all the stuff, all those test patterns, a lot of those test patterns I developed 2 or 3 years ago. And they're still useful because I seem to be the only one that has them. And I seem to be the only one that's at my level. And I think in my mind I'm still at a horribly basic level. You know, I'm just scratching the surface. But this in 2160p, we had the privilege of having this on a 20-foot wide screen in 2160p, or in a higher resolution. And the people who were looking at it looked at me and said, gee, this begs for a much bigger screen. They weren't happy with a 20-foot wide screen. They wanted a much bigger screen. They recognized that in 2160p, this content could easily drive a 50-foot wide screen, and they wanted it at 50 feet. All right, 2160p is 3840 by 2160. It's exactly twice 1080. I'm calling it 2160p because that is the appropriate name for it relative to the way we've named every other television system we have. We have 480, 576, 720, 1080. This is 2160. Yes, and it's a 1:8:5 aspect ratio, and or 1:8:9. I'm sorry. If you look into, and Ron covered this in the luncheon, 4096 is a production format, and it describes horizontal resolution. There is no fixed number for vertical resolution in the 4K system. And the vertical resolution is dependent on the aspect ratio. And 4K is the only common number among all the uses of the 4K system. So it's called 4K. But if you're doing a 133 image, it's 4096 by 3070. If you're doing 178, it's 4096 by 2306. And you get the idea. So, but our television system is 178 aspect ratio now, and so I'm calling our new system 2160p because in the convention of the way we've named every other system that we use, that's what it is a 2160p. So, and I also want to make sure that it is clearly differentiated from the 4K system. 4K is 4096, and of course, 2160p is 3840 across the top. There's a 6% difference, 3% on each side. Do you remember when I showed you the pixel-based test pattern and I zoomed it out? I zoomed that out 2%. Do you remember how bad the picture looked when I zoomed it out 2%? It is almost impossible to convert 4096 to 3840. If you want a good picture, you literally have to take a center cut. You literally have to take 3840 out of the center. And that's the reason I don't want it known as a 4K format. I want it known for what it is. It's 2160. And if people don't understand they are two completely different formats that are not compatible, we're going to be in a lot of trouble. So that's what I've been doing instead of developing new test patterns for 3D.
Which kind of camera are you using here?
This is the Nikon D90 that took most of these pictures. It is it's 45 something along horizontal. Of course, this is 3840. So I actually all that panning and scanning, I took a 1.5 image that had more resolution, and I just panned and scanned it. But this is the first piece that I've ever produced in 2160p, and it's the only content I had. The joke of 2160p is everybody's saying, well, who's got content? Anybody shooting DSLR has got content. The camera that Herman had, this is an 8K camera. So I can shoot at twice the resolution of 2160p. So I can shoot at twice the resolution and down convert and get a really good picture. Thank you. And so that I had to buy a new camera because now I'm doing 2160p, and I have to start out at least twice the resolution before I'm going to be happy. That guarantees me lots of detail. Anyway, those are the kinds of things I'm doing. I hope this has been helpful.
You didn't mention any motion effect of the 3D. Other cameras are kind of
I am not at the point of doing motion patterns up to this point. I actually found a generator that would take my patterns and put them in motion, and found all of the standard LCD blur issues that I found with 2D. In other words, so far I haven't found anything in 3D that I don't already know about in 2D.